biggest angle. And if I was going to draw a diagram of this, here's your incident ray. The reflected ray has to make an equal angle to the incident ray. And then it refracts into the air out here. So the question is, does it bend away from the normal line or towards the normal line? And the answer is away from, because we're going from high to low refractive index. So this one will bend like this. So what's the biggest angle? This one would correspond to option C, this one would correspond to option A, and this one would correspond to option B. All right. Unfortunately, it looks like somebody stole my power cord, so I cannot run the demo that I wanted to run. Oh well. Anyway, we're going to look at spherical mirrors. We're going to look at spherical lenses, thin lenses, and we want to see how each one of them forms images. Spherical mirror, the basic idea is that you have a sphere of some material and you've coated it with reflecting material like silver or gold or aluminum, depending on your wavelength. And what you've done is you've taken a slice of it. So we slice off one piece of the sphere, and we get rid of the entire rest of it. And so here's your mirror. And you've either silvered this side of it so that it reflects off of this, or you've silvered this side of it so that it reflects off of this. And in both cases, you use the law of reflection in order to figure out where incident rays will reflect to. So for example, I have one axis which runs like this, that actually runs through the point that would be called the center of the sphere. So if I left the sphere present, this point would be C, and this distance from here to here would be distance R, because it's the radius of the sphere. And if I send a ray along this one axis, it's going to hit normal to the surface. In other words, it's going to be incident at a 0 degree angle. If it's incident at a 0 degree angle, what is the angle of reflection going to look like? If theta I is 0, what is theta R? What angle would theta R be in this case? have to obey the law of reflection. And the law of reflection says that this angle and this angle should be equal. So this one also ends up being 0 degrees. That means that the ray basically would do this. It would come in like this, it would hit here, and it would bounce back right along that axis again. Okay? Only the ray which is actually on that axis will do that. Because that's the only ray that will actually be perpendicular to the surface when it hits the mirror. So this axis is sometimes called the principal axis. All right, so the principal axis has the property that a ray which travels along the axis, not parallel to it, but actually along it, will reflect back along the same path that it came in from. It is defined as the ray that goes through the center of the sphere to the vertex, or to the point where a radial line would touch the mirror. And in fact, any ray which originates at the center and then reflects back will do this retroreflection. So if I have a ray that's here and it comes like this and hits the mirror, it will also reflect back this way. Any radial ray will do that. What do the other rays do, though? What do the other rays do? What other rays? Well, let's redraw our diagram so it's a little less cluttered. I'm going to draw the mirror a little bit bigger and slightly exaggerated. So here's my mirror. Here's my principal axis. And my incident rays will all be parallel to this mirror. I'm not going to draw the one that goes along the principal axis for the simple reason that we already know what it's going to do. What will these other ones do, though? Well, they also reflect off. And they also obey the law of reflection. And it turns out that the law of reflection for each one of these rays will send it to the same location. So this ray will reflect off like this. 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 So all of them have come to the same location right here. That location where all these rays have reflected through is what's called the focal point of the mirror. All right, so sometimes we label it with an F for focal point. And the distance, we use a little f, is what's called the focal length. All right, so all these rays pass through the focal point. How far is the focal point from the mirror? How far is it? If you eyeball it, you see that it's about half of the distance to the center point that I drew here. And in fact, it turns out for a good spherical cross-section of mirror, F is in fact half of the radius of the sphere. Okay, so what this allows us to do is, if we wanted to design a mirror with a particular focal length, we do it by saying we're going to make a sphere of a particular radius and cut off the end of it. And that will give us the focal length that we need. Why would we need a particular focal length? Well, if you want to make, for example, a telescope with a mirror, you have to have a pretty particular focal length to make the telescope work. And it depends on how long your telescope is and how much magnification you want and so on. All right. Now, there's two types. I've been drawing the diagram that goes with what's called a concave mirror. It's sort of like all the rays are entering a cave before they hit the back of the cave, which is the mirror. It's concave. The other type is called convex, and that's what would happen if the rays came in from this side instead of from this side. And if that were to occur, instead of passing through the focal point, they'd actually reflect away from the focal point. So if we had a convex mirror, our rays would basically do this. And instead of reflecting back this way, they reflect off this way. You see the rays are basically spreading apart. I've drawn this one badly though. There we go. The rays are basically spreading apart. And if you look along these rays, the point where they would converge, if we drew a dashed line, is the focal point of your convex mirror. And it turns out that the focal length still obeys the same rules as over here. It's still 1/2 of the radius of curvature. It just happens to be on the opposite side of the mirror from where the rays actually are located. Now, how do these things form an image? How does a mirror form an image? We can draw a ray diagram, see how that works as well. These ray diagrams only are to illustrate where a focal point is. For imaging an object, we need a new type of ray diagram. A new type of ray diagram, we want to actually label for ourselves a few of these points that I've already shown, namely the vertex, the principal axis, the focal point, and the center point. Here's the mirror once again. Here's our principal axis. We'll make our focal point be here. We'll make our center point be here. So how do we get an image formed by this mirror? Well, in order to have an image, we need to have an object that the mirror is actually imaging. In order to have an image, we have to have some object that the mirror actually images. And if we have an object, then that object is going to be placed at a particular location relative to the mirror. You know from looking at, for example, the flat mirror that's probably in your bathroom. You look at that, and if you stand closer to it, your image gets closer to it. If you stand farther away, your image stands farther away from you. So something similar could happen here. Where you place the object determines where the image will be formed. So where do we want to place an object? It could be anywhere. It has to be somewhere on this side of the mirror, of course. You can't stand inside the mirror. Let's place the object right here. And to make our diagram easy, the object that I'm going to place will just be sort of a stick figure or an arrow. Now I need to draw some rays that come off of this object. What rays could I draw? Well, I could draw any number of rays. But there are a few that are actually helpful for figuring out where the image will be located. So I basically stuck it so that it's an equal distance away from the center as the focal point is. It just happens to be on the opposite side of the center. So let's draw a few rays. First ray that I'm going to draw will be one that's parallel to the principal axis. The ray's parallel to the principal axis. Where is this ray going to reflect to? Where will the ray reflect to? Through the focal point. So this ray has to reflect such that it passes through here. That is how we define the focal point. Whoops, kind of bend it a little at the end, but oh well. Now I need a second one. Second ray, I'm going to go ahead and draw going through the focal point. Where will that ray reflect to? So I'm going to draw this one going through the focal point like so. Maybe a little off of my aim, but basically just went through the focal point. It's got to reflect parallel to the axis. In other words, these reflections are sort of reversible. So this ray has to reflect parallel to this axis. All right. Let's draw another ray. Let's draw one that goes through the center point of the axis. All right. A little bit wavy. There's better. How's that one going to reflect? So I just drew it so it passes through the center of the circle. That means that it is a radial ray. So how will that one reflect? Based on the rules that we had earlier. It has to reflect back along the path that it passed through initially. And we've actually drawn enough rays at this point to figure out where the image is, but if we wanted as an additional check, there's a fourth ray that you could draw with a mirror. It's basically the ray that goes to the vertex. And the way that that one works, you draw it so it heads over to the vertex like so. And then this angle and the angle for the reflected ray should be equal to each other. So it reflects off the vertex about like that. So this angle and this angle are equal. Now, what do you notice about all these reflected rays? Anybody? They all sort of hit at the same point. And if I was a little better with the diagram, or if I used an actual straight edge and measured my distances more precisely, I think we'd find that they actually hit at exactly the same point. Okay, so they all cross right here. So what's special about that point right there? That's where the image is going to be. That's where the image of this thing is. And so our image looks like this. All right, what do we notice about this image? We found where it is. It's still going to look like an arrow because in principle we could draw these lines for every point on the arrow, but you can imagine that's going to clutter the diagram a bit. What do you notice about the image that's been formed? It's upside down. Okay. So upside down, what we say in optics is it's inverted. So we have an inverted image. What else do we notice? It's actually, yeah? Yeah, it seems to be more or less midway between F and C. And it may actually be exactly midway between. We have to measure more precisely to know for sure. Good observation. In other words, we're able to figure out where it's located. If we were to measure, say, this distance, then we measure this distance, then we know where it is. Okay, anything else that we notice about it?
The edge touches where all of them, like the tip of the arrow.
That's true. But it's because that's what we're trying to image is the tip of the arrow. It's a true statement, though. That is where that, we are finding the location of the tip of the arrow's image. But it turns out if we want an image like this part, we find that it is in fact right here and so on. There's actually two other things to notice. One of them is sort of something we've said already, which is that these rays all really do pass through this point. So we would say that this is a real image. There are actually two types of image, real and virtual. What would a virtual image look like if this is a real image? What would a virtual image be? Well, a real image is where the rays really do pass. What this means is, among other things, if you took like a card or something and you put it right here, you really could get an image that forms on the card. It works really well if, and this is why I wanted to bring this, but unfortunately no power supply to show this to you today. If you take like a candle or maybe a light bulb, which is what's inside of this, and you image it off of a mirror like this, and you get a real image, it means that if you put the card where the image is formed, you'll see an actual flame. Or you'll see an image of a flame or of a light on the card, and it will be very sharp. Well, as sharp as your original light or candle is, roughly. Okay, so that's what a real one is. A virtual one, you can't do that with. What would a virtual image look like for a mirror? The answer is, it looks like the kind of image that you see when you actually go to your bathroom and look at the mirror that's over your sink or wherever you put your mirror in your house. You look in the mirror and there's an image in the mirror looking back at you. That's a virtual image. If somebody goes behind the mirror and like holds a card or whatever, wherever that image is formed, there's nothing on the card. There aren't any real rays of light making it to that point. You only virtually make it there. Does that mean that that image doesn't exist? Well, no. It exists. If you take like a camera out and take a picture of the mirror, you'll get a picture that has that image in it. It just means that you can't put a card there and see it show up sharply on the card. You can't shine a light at a mirror and stand behind the mirror and see the light come through, in other words. Okay, there's one other thing to notice about this, which is smaller. The image is smaller than the object that's producing it. All right. The ratio of the size of the object and the size of the image is what's called magnification. In this case, it's actually called lateral magnification. The definition is that it's the ratio of the height of the image the size of the image, to the height or size of the object. So this distance right here would be height of object. This distance right here would be height of image. And it turns out that if you were to calculate this magnification for these two things, you'd get a negative number. Why is it a negative number? Because the image is inverted. So if you get a negative number for your magnification, it means you're going to have an inverted image. If you get a positive number, it means you're going to have an upright image. Now we can do this from the ray diagram, but there's also an equation that you can use to similarly locate it. The equation looks like this. 1 divided by the distance to the object, I'm going to shorthand it as dO, plus 1 divided by the distance to the image, di, is equal to 1 divided by the focal length for the mirror. And the magnification is the negative of di divided by dO, where these distances, you already have the focal length. The di would be this distance right here, distance from the mirror to the image. And dO is the distance from the mirror to the object. All right, so let's do a quick example with this set of equations. And we'll do the example as a sort of double check because we just drew one. Suppose your mirror has focal, let's say has a radius of curvature. Let's make it a nice easy number. Let's make it 1. All right. Suppose further that the object has height. Now this is obviously somewhat less than 1 meter. So this right here is approximately 6 centimeters. We'll treat it as if it's 12. In other words, like pretend like this is a half-scale model. All right, and placed. How far away should we place it? Let's place it a distance f plus c away. F plus r. Describe the image. That'll be our example. All right, so what's the first thing we have to do in order to get this example to work out? Well, I told you what the radius of curvature is. This right here would be r. So I told you that the distance is r plus f. So I think the first thing we got to do is figure out what f is. So f is the focal length. And I wrote over here your equation to get the focal length from the radius of curvature. It's half of the radius of curvature. So since f equals 1/2 r, That makes it 1/2 of 1.0 meter, or 0.5 meters. All right, so now we know how long the focal length is, and therefore we know what the object distance is. DO must be 0.5 plus 1. Now we need to figure out where DI is going to be. Let's use this equation. All right? I'm going to leave my diagram though because I want it for later. So this equation says 1 over DO plus 1 over DI is 1 over F. If I solve it for 1 over DI, that means 1 over DI is 1 over F minus 1 over DO. Numerically, that's 1 over 0.5 meters minus 1 over 1.5 meters. So what does that mean that 1 over DI is? This is where your calculator should be coming out if you don't know how to do it mentally. Or if you don't want to do it mentally. Okay, so this one right here you should be able to do without the calculator. 1 over 0.5. That's 2. Now we subtract from that the 1 over 1.5, which I think should be 2/3. So 2 minus 1 over 1.5. And this collectively gives us 6, 7. That's 1 over DI. We want DI. We want to know what the actual distance is. So DI is the inverse of that, and that is 0.75 meters. First, double check here. You said a minute ago, it looks like the image is formed midway between the focal point and the center. We just calculated it as 0.75. Sure enough, that's midway between the focal point, 0.5, and the center, 1.0. So sure enough, it is in fact midway between the two of them. Now we need to know what the magnification factor is. Well, the magnification factor should be negative DI over DO. Well, that would be negative of 0.75 meters divided by 1.5 meters. Or in other words, negative half. So it's half as big as the object and it's inverted. Do these things compare favorably with the diagram that we've drawn? I'd say so. The diagram suggests that this should be about midway between the two. The calculation also says midway between the two. The diagram says that it should be inverted. The calculation says that the magnification is negative and therefore it's inverted. The calculation says that it should be about half the size of the object. The diagram says it's about half the size of the object. One other prediction, though, that the diagram makes, and then we have to ask, does the calculation hold this prediction? Real or virtual? So our diagram says it should be real. How do we get that information out of the calculation? Whether it's real or whether it's virtual. Ideas? It's actually there for us. What we do is we look at the sign of the answer for the image. If it's a positive number, that means that we have a real image. If it's a negative number, it means we have a virtual image. And we have a positive number here, so that matches our expectation that we get a real image. Question: is it possible with this kind of a mirror to get a virtual image? Is it possible with this kind of a mirror to get a virtual image? We see that it's possible to get a real image. Can we get a virtual image? The answer is yes, we can. How do we do it? Where would we have to put the object to get a virtual image? So there's two ways of answering this. One is we could do it with the calculation. The other is that we could try to draw ray diagrams for it. Visualizing what the ray diagram looks like might be a bit of a chore without drawing it each time. But you can do it from the calculation. The thing is that what you need to get a virtual image is a negative answer. How do you get a negative answer? Well, this number has to be negative, and in order for that to happen, this collectively has to be bigger than this collectively. And in order for that to happen, DO has to be smaller than F. In other words, if I place the object at, say, 0.25 meters, then this calculation would suddenly show 1 over di is 1 over 0.5 minus 1 over 0.25. But that's 2 minus 4, which is a negative number. And since that's negative, it means that the image formation will be virtual. Yes?
Since we're still at the 7 minutes, are you going to reschedule our
The quiz? Yeah. Yeah, I will. Thanks for reminding me, though. So this right here will give us a virtual image. Means the image will be formed back here somewhere. Now here's a few things to note about these images. If it's a real image, it will be inverted. If it's a virtual image, it will be upright. For this type of mirror, the concave mirror, virtual images are often larger than the object. Real images often are smaller. Now you can work out, is it always larger and is it always smaller? You basically have to do some limits. And you can do that as a practice if you like. What I haven't done is what happens if we have a convex mirror. And it turns out that if your mirror is convex, then it will only form, at least for this simple setup of one mirror and one object, it will only form virtual images. You will not get a real image from a single convex mirror. Furthermore, the image will always be smaller than the object for a convex mirror. For lenses, in some sense, you get the opposite effect. A convex lens will always form a virtual image, which is smaller than the object. A biconvex lens always gives you the possibility of a real or of a virtual, depending on the object placement. On that note, I guess we're out of time for today.